Assalamu alaikum and welcome to lecture number 33. In this lecture, we are going to summarize the course which we have studied up to now. So to summarize, we can say we have these topics covered in this course we have talked about the signals, and then we talk about their classification. The next topic was systems and their classification, or we can also say systems and the properties of the system. Then the next topic was the time domain analysis of LTI systems, where we talked about the LTI systems, and we said that knowing the impulse response is sufficient to characterize the LTI system. And we said if we know, and we talked about it, and we proved that if we know only the impulse response of the system, then we can tell whether the given system is causal, non-causal, memoryless, or has memory, or is it stable or unstable, and so on. The next main topic we discussed was the frequency domain analysis and synthesis, and in this chapter we talked about the continuous time and discrete time Fourier series and Fourier transform. The last topic we discussed was the Laplace transform. So let's have just a brief overview of it. So starting with the signal, uh, the first thing is what is a signal. So we defined a signal as a signal is defined as a function of one or more variable that conveys some information on the nature of the physical phenomena. Then such signals can have one or more than one independent variable. So depending upon the number of variables, we can call them their dimension. For example, if a signal has only one independent variable, then we call it a one-dimensional signal. And those signals that depend on more than one signal, in general we can call them multi-dimensional signal. For example, if we have a binary image, or if you have grayscale image, then grayscale image has two independent variables, that is x and y. So such a such a signal which is a grayscale image is called a two-dimensional signal. We can also have more than two-dimensional signal. So for example, speech is an example of one-dimensional signal. Okay, and in case of time domain, we say that the independent variable for the case of time domain, the speech signal has t as independent variable. Mathematically, signals are represented as a function of independent variable, for example f of t. So here f is a function or a signal of the independent variable t, right? So in this case we can say this is a one-dimensional signal because there is only one independent variable. Similarly, f of omega is a function of omega, and because this is a single variable, single independent variable, so we call such a signal as one-dimensional signal. So that means one-dimensional or multi-dimensional signal can be in time domain and can also be in frequency domain. Similarly, the third example here is the intensity value. So we can see that it is a function of two independent variable. So in this course, as we said, we'll talk about only the one-dimensional signal. So one-dimensional signal can be, so the independent variable can be a frequency or time. Then we classified the signal into the following 5 classes, that is continuous time versus discrete time signals, right? So the independent variable can be continuous or can be discrete. So if the independent variable is time and it is continuous, then we call it a continuous time signal. Similarly, if the independent variable is time and it is discrete, then we call such a signals as discrete time signals. The another category was the signal even and odd. So we defined it as signal is said to be even if the time reversal and the original signal they are same. And we find we can do it using mathematically. We can find the even and odd parts of a signal, or we can also do it using graphical that we have already discussed in detail. Similarly, signals can be periodic or they can also be aperiodic, right? For the odd case, they are the reflected version uh, of the signal has reversal in amplitude also, so then we say that it's a odd signal. Okay, periodic and aperiodic signals. So you understand periodic signals can be continuous in time and they can also be discrete in time. Then the next category was deterministic signal and random signal and the energy and power signals. So here is an example of the continuous time and discrete time signal. So you can easily observe that in case of continuous time signal, the signal has continuous values or it is analog. Whereas in case of discrete time signal, the signal has values only at discrete interval of time. The next thing we discussed was about the operations performed on independent variable. You understand, in case of one-dimensional signal, we have one independent variable, right? Which is, if we are in time domain, then that is t, and if we are in frequency domain, then it is a frequency. And one is the dependent variable, which is a signal itself. So we talked about three different operations on the independent variable, right? So that is like the shifting. So we can shift a signal to the right or to the left, right? So that is the shifting, right? So you know that t naught represents a shift. So if t naught is positive, then the resulting signal will shift to the right by amount specified by T naught, and if T naught is negative, then the resulting signal will shift to the left. So similarly, for the discrete time case, we have N naught as a shift parameter. So depending upon the value of N naught, it can shift right or left, and similar arguments apply to what we already discussed for the continuous time case. The only difference is that in case of discrete time signals, the shift parameter and not can have only the integer values, right? The next operation is the uh, scaling operation. So here we can say that y of t is the scaled version of x of t, right? And what is the scaling factor? It's a of t. So you know that if a is greater than if a is between 0 and 1, then the resulting signal, which is y of t, it will be uh, stretch. And if a is uh, greater than 1, right, positive values, if a has positive value and greater than 1, in that case the resulting signal, which is y of t, will be the compressed version of x of t, right? In case a is greater than, for example, a is equal to, for example, -2, in this case the resulting signal y of t will be compressed, but it will also be reflected version of y of t, right? So I hope this gives you idea. This is an example of the signal that is uh, reflected version, right? This is x of t, and reflected version of x of minus t is this one. So again, talking about the system, so we defined a system that is anything that generates a signal or transmits a signal, receives a signal, processes a signal, and so on, right? So systems are used to process signals, to modify or extract information from the signals. And we can also say systems process a set of signals to yield another set of signals, right? We represent a system by the way it transfers an input signal into an output signal. So a system can be made up of physical components, such as for example, in electrical mechanical systems, right? Or it can be algorithm that computes an output from the input signal, that is software, right? So systems transforms the input into output. So for the case of continuous time, we have, for example, x of t as input signal and y of t as output signal. So arrow here represents the system, that is some operation, right? Similarly, for the discrete time signals, we have discrete time system. Systems are represented by the block diagram. They are also represented by mathematical equations such as this one, or they can also be represented by operations such as y of t equals to some operator h, which is applied on x of t, or for the case of discrete time, we can say that y of n equals to h, an operator performed on some signal x of n. So classification of systems, or we can also say the properties of the system. So some of the properties of the systems are whether a system has memory or it's without memory, is it memory less or with memory, or we can also say the other, right? The other property, for example, is the system stable or unstable? Is the system causal or non-causal? Is it invertible, non-invertible, time variant, time invariant, linear, or non-linear system, right? Then we talked about the LTI system. So in case of LTI system, we say the impulse response is the thing which can tell or describe the whole uh, LTI system. If we know uh, impulse response, so we can completely characterize the behavior of the LTI system. So we have two basic facts. For the LTI system, the response of linear system to an input x of n will be the superposition, right? X of n for the continuous time, for the discrete time case, and x of t for the uh, x of t for the continuous time case, and x of n for the discrete time case, right? So that is, we have the system holds the property of linearity, that is, it holds the superposition and scaling. And the other important thing is the system is time invariant. The response of the time invariant system to the time shifted unit impulse are simply the time shifted versions of one another, right? So if a system holds these two properties, we call such a system as an LTI system. And as I said earlier, for the case of LTI system, the impulse response completely characterizes the behavior of the LTI system, whether the LTI system is discrete or continuous, right? For the case of discrete LTI system, using the convolution sum, we can find out the output of the system. Or for the case of continuous time LTI system, using convolution integral, we can find the output of LTI system. Because we say that impulse response completely characterizes the behavior of LTI system. So that means if we know the impulse response, we can tell whether the system is memory less or it has memory. So for the case of discrete time system, it is defined as h of n. If h of n equals to 0 for n is not equal to 0, then such a system is called the memory less system, right? For the continuous time case, we can write h of t equals to 0 when t is not equal to 0. So if this is the case, then we say the system is memory less. If this is not the case, then we say system has memory. Similarly, for a system to be invertible, these are some of examples of the property we have discussed in detail in our lectures, right? So invertibility, if two systems are invertible, then if they are cascaded, that means if they are put in series, their impulse responses for example, one system has impulse response h of t and its inverse system has impulse response h1 of t. So if they are convolved, they will result into impulse. So if two impulse responses after convolution results into impulse of t, that means the two systems are invertible to each other, right? So for the discrete time case, we can write that h of t, h of n convolved with h1 of n, right, will result into impulse of n. So if this is the case, then we say the two systems are reciprocal of each other, are invertible, right? One system is reciprocal of other. Then we define the causality. So if you recall, for a system to be causal, the impulse response must be equal to 0 for when its argument is negative. For the negative argument, the right, so you understand, for a continuous time case, the argument is n, whereas for the for the discrete time case, the argument is n, and for the continuous time case, the argument is t. So if h of t equals to 0 when its argument, which is t, is negative, then such a system is called as the causal system. Or if we talk about the discrete time case, so h of n must be 0 when its argument is negative, then we say such a system as causal system. If h of n is not equal to 0 when n is negative, in that case the system is non-causal. So you understand that knowing only the impulse response, we can tell, or we know the whole behavior of the LTI system. Similarly, for stability, we say if its impulse response is absolutely summable. What does that mean? That means if I sum this, because it's the discrete time case, so in discrete time case we use the summation. So if I sum this impulse response, which is h of k, from k running from minus infinity up to infinity, and it does not diverge. Diverge means it means that we get some finite value. So if I get some finite value when I sum the response from minus infinity up to infinity, then such a system is called as stable system. Similarly, for the continuous time case, if I integrate the h of t, absolute of h of t, from minus infinity up to infinity, in that case it's star, right? So if you write tau, whatever is the independent variable, okay, it's same if you take t or if you take tau. Okay, so if we're taking tau, so that means if tau is from minus infinity up to infinity, and this results into some finite value, then we call such a system as stable system. But in case the impulse response results into, right, the impulse response, that's the absolute integration of the impulse response from minus infinity up to infinity, results into some infinite value, then we call such a system as unstable system. Okay. Then we came to the next topic. In the previous topic of LTI system, we said if we can represent a system in terms of signal, in terms of scaled and shifted impulses, then knowing that the system is LTI, we can find the output of the system using the convolution, right? So then in next chapter we talked about the Fourier series and Fourier transform. So in case of Fourier series, we have the analysis equation for continuous time and discrete time as AK. AK are the Fourier series coefficients, and this is 1 over t. T is the period of the periodic signal. You understand the Fourier series is used only when the signals are periodic. In case the signals are non-periodic, then we use the Fourier transform. So in case of Fourier series, we have periodic signal. So that means we have, this is the expression, we multiply by this and integrate it over one period, right? You understand, over one period can be from 0 up to t, right? From 0 up to t, or you can also, right? So from 0 to t, or you can also take from minus t by 2 to t by 2, or you can also say t2 t2, right? T up to 2t. So you understand that integration is just over one period. So one period is whatever seems easy for you. Okay, similarly for the discrete time case, again this is the expression. So you can say that analysis equation basically is used to convert the time domain signal into frequency domain signal, or you can also say that basically the analysis equation is a method that splits the signal into its constituent frequencies, right? So normally we say just like the it's like a prism, like when a light falls on the prism, it splits the light into its constituent parts. So similar is the analysis equation that tells you about the uh, component of the signals that it is composed of. So we can also say that analysis equation basically splits the signal into its constituent parts, right? So you understand, we have studied that signal can be discrete or can be continuous, right? And the other classification was periodic and aperiodic. So you understand that both the signal, whether continuous or discrete, can be periodic or aperiodic. So we use the Fourier series or this analysis equation only for the continuous time periodic signal, and this one for the discrete time periodic signal. So I hope you understand, right? Similarly, this is the equation for the synthesis equation. Synthesis means that you combine the individual parts to make a something whole, right? So this is for the continuous time case, and this is for the discrete time case. You also understand that k has integer values, right? So that's why we can say that the resulting spectrum or the coefficients of the Fourier series, they are discrete, right? So it will be something like one coefficient is here, for example, starting with, depending upon, right, this is 0 and this is k times omega naught, right? So for example, depending upon whether a signal has, like if you have some waveform like this, so this waveform has some sorry, let me, okay, uh, right? So for example, we have some waveform like this, right? So by looking at this, you can say that it will have a DC value. DC value is the every value over one period, right? So the k equals to 0 represents the DC value. So if it consists of some DC value, so it will be plotted here. So the next value will be k equals to 1, whatever value, whether it's positive, negative, whatever it is. I'm just trying, this is not the uh, Fourier series, right? For, right, this is not Fourier series coefficient for this signal. I'm just writing the generalized one, right? So the position of these coefficient will be at discrete frequency, right? So it's not continuous one. So the resulting spectrum, this graph, it will be a line spectrum, right? In case of Fourier transform, which we have studied, in that case the resulting spectrum is continuous, right? You also know it can have negative values, something like this, right? So we have coefficients on both right and left side, or negative at negative and positive frequency. So I hope this gives you some idea. Okay, similarly for the case of continuous time, I mean aperiodic signal, for the case of aperiodic signal, we use the Fourier transform, and this is the expression for the Fourier transform, and this is the analysis equation. And we can also say, again, just like the coefficients ak of the Fourier series, which we call them Fourier series coefficient, x of j omega is also complex, right? So if something is complex, that means it has its real part and imaginary part. You understand that complex numbers are represented in two format, generally in two format, that is the rectangular form, which in which you write the real and the, for example, we have a I'm talking about the constant, right? So we have a constant z, which is a complex, so it has the expression a plus j b, right? So this is uh, rectangular or the real and imaginary representation. We also have the other one in which we write z as z magnitude times angle of z. Okay, so z magnitude, you understand, can be found by squaring the real and imaginary part and taking the square root. So we have two different notations, right? So this one we also say the magnitude, right? This is the uh, magnitude, right? And this one is phase. You understand, phase of z, for example z x of j omega. You understand the difference between z and x of j omega, right? Because z was constant. You did it maybe in metric or you have FSC, but now you understand the this complex is number is variable, right? So it changes. So what is, how it is variable, when it will change, it might change. In general it changes with the frequency, right? So that means the magnitude is also variable. In this case, magnitude will be variable at different values of omega. It will have different values, and the phase is also variable at different values of omega. It will have, so the expression for this is tan inverse of uh, imaginary over real, right? Imaginary over real. And because here the real and imaginary, they are function of omega, so they will change with omega. So the resulting thing will be a graph. For example, we have something, we have done this for, I think, low pass filter, if you recall. So it was something like this. It was going like this, and again it's not exactly that because it's difficult to draw the accurate graph with the mouse, but it's something like this, right? So that is the magnitude of, and we represent magnitude by x of j omega and two bars here. So that represents the magnitude. So you understand frequency can have negative value and positive value, and depending upon the value of x of j omega, you put different values of frequency. This we have done in much more detail. Similarly, for the discrete time case, right? The Fourier transform of the discrete time signal is given by this expression here. Capital omega represents the frequency of the discrete time signal, right? So this is the analysis equation, and this is synthesis equation. Again, this is the synthesis equation, and this is analysis equation. You can also say the analysis equation, or you can also say equation that transforms the time domain signal into the frequency domain. So if you look at this one, this is your time domain signal, and you are converting it or transforming it to the frequency domain. And this is the frequency domain signal, and you are transforming it or converting it to time domain, right? So you can also say converting the time domain, converting the frequency domain into time domain, or you can say converting the synthesis equation, right? So this is the analysis equation for the discrete time aperiodic signal, and this is the synthesis equation for the discrete time aperiodic signal. So the last thing we did was the Laplace transform, and Laplace transform has the analysis equation, which is this one. This equation is used to transfer the time domain signal into the S domain, whereas this equation is used to convert the S domain signal into the time domain signal. If you compare this with the Fourier transform, so in case of Fourier transform, we said x of j omega, right? And that is equal to integration minus infinity up to infinity and x of t e power minus j omega t and d of t, right? So again, you see that frequency is uh, uh, we are integrating it from minus infinity up to infinity, right? And the this one is the exponential complex exponential that is multiplied by this one. So if you compare this with this one, the only difference is that uh, instead of omega, right, we have, this is Fourier, so we have omega Fourier, right? And for Laplace we have s, and if you look at s, basically equals to sigma plus that's basically j omega, we can write it, right? Sigma plus j omega. So if you compare, so you know that in case of Laplace we have this uh, real part also. In case of Fourier, here the real part is basically 0. So I think that's all for the course, and let's discuss it in the live session, and let's see uh, how you, how much you have learned it, and how is your comments about the course. So let's meet you in the live session. So that's all. Allah Hafiz.